Okay, today our speaker is Mariel Sáez. We already know her a few years ago. She came here to Granada and gave us another talk, I think. And today her talk is going to be about some flows or something. Sorry, I don't remember the title. But so whenever you want to, you can start.
Okay, I'm gonna share my screen. I'm gonna try to share my screen. So what I'm gonna talk about today is some existence and result on the network flow, and this is joint work with Jorge Lira, Rafe Maceo, and Alessandra Pluga. Okay, so I had the talk somewhere here, and now I cannot find it. It's the technology. I think I closed it by mistake. Let me see if I can find the talk that I had prepared some pictures already. I don't know what happened with this. Sorry, some of the issues with technology. So if not, I'm just gonna go without that. I don't know what I did. Sorry about this. It's gonna work anyway. This is weird. Sorry. I don't know how. Anyway, I think I'm just gonna go like this, and you will have to deal with my bad drawings, because I did some drawings before just not to make mistakes when I draw, but I think it's gonna work somehow, and now the application closed. Okay, so I'm going to start by trying to describe the title. So what is a network flow? I'm going to start by trying to describe what is a mean curvature flow and curve shortening flow a little bit. So many people here are already familiar with this, but mean curvature flow is the gradient flow of the area functional. So by that I mean it's sort of the parabolic version of the minimal surface equation. So what I'm gonna be considering, this can be done more generally. So consider an embedding. Embedding. From some manifold, some n-dimensional manifold cross a time variable into an ambient manifold that for me is always going to be Rn+1. And then in general, what the equation would say is that if you take the speed of this embedding times the normal vector, this should be the mean curvature. So this here represents the mean curvature. And if you write this as a PDE locally, this is a parabolic PDE. And then you can think about existence and uniqueness in some sense that I'm gonna be more precise later. this context when you're talking about things that are smooth. So if it's regular, it's a embedded smooth manifold, standard theory would give you existence in general. Standard PDE theory is going to give you existence. I want to say implies. Okay, so I'm gonna be mostly focused in the case that n is equal to 1. So x is a curve. Just because I'm used to this, then my curve is gonna be called gamma, but because the curves for me are gamma usually. So gamma is a curve. It's a curve that satisfies then, when this is just one dimensional, that is going to be the case that we care about today, that the gamma dt times the normal is actually the only curvature that you have. So it's okay. And the sign there, it depends on the orientation of the normal that you're choosing. So if this is the outward normal, then you get minus k. If this is the inward normal, you can write there plus k. So there's some choice there that we're making with the sign there. But they should be understood as something convex should be converging to a point. I'm just saying that. I'm gonna give an example just to set my notation maybe. That is, if you take a circle, and this in general, if you take a sphere, then the speed is gonna be the same in all points. And you can expect then that you would have an evolution that is just something that the radius is changing. So my gamma t is gonna be something like this, and here omega, because it's one dimensional, I'm thinking just, I don't know, cosine theta, sine theta. In general, this is gonna be something in Sn. And then if you plug this into the equation, you're gonna see that the radius is gonna be square root of whatever your initial radius was, minus 2. So even from this simple computation, this is very simple to get if you just plug it into the equation. You see that in finite time, this is converging to a point. So we can see that in finite time, the circle is converging to a point. So even in this very, very regular case, you get that the circle is getting smaller, 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 and eventually is becoming a point. So even in this very regular case, you have a singular behavior at a finite time. So see, this is singular in finite time. So a lot of the study of the mean curvature flow is around understanding singular behavior, how the singular behavior happens, whether this is the worst that can happen or not. And well, the exception is not gonna be today. I'm gonna talk about certain singular behavior in a particular case that is more complicated than that. So having said that, just sort of for completeness, I'm gonna say that all this that I had done before, that in general, for curves, for embedded curves, we have that in finite time, they become convex. It is known that if they're convex, they have the behavior that I described before. if they are convex, they shrink to a point in finite time. In finite time. And after rescaling, this point it looks like a circle. Scaling. The point is the point, and this is what they usually call that is round. This is a result by Gage and Hamilton of the mid-80s. So this is due to Gage and Hamilton. I think it's 86 in the paper. And there's a later paper that shows that if the curve is not convex, it becomes convex in finite time. And then you can apply the previous result. This is due to Grayson, and it's like a year later. For higher dimensional mean curvature flow, actually the first result is true and it's due to Husken. In higher dimensions, but the second one is not true and you have more complicated singularities. And there are examples, there are many examples. This is Husken. But not the second. And the reason why I'm mentioning that is because then there are many notions of weak solutions that you can do for mean curvature flow in order to, when you run into singularity, how to continue the flow. So, and most of these things are tailored for higher dimensions because this is the case where they happen mostly for smooth embedded surfaces. And this is the case where also these weak solutions have been mostly studied. But you can also apply it for the one-dimensional case. So there are many notions of weak solutions, and I'm just gonna mention one because it's the one that is gonna be relevant today, although there are many others. And the one that I want to mention today is the one due to Brachie. Notions of solutions for mean curvature flow. Probably the most standard one are this one, the one due to Brachie, and the level set flow. And the level set flow, for instance, is something that is not going to apply in our citation. For mean curvature flow, one is due to Brachie. And what he does is he tries to pose the problem in the sense of geometric measure theory, which he's allowed to evolve variables, things that are much more general than just embedded smooth manifolds. He generalizes the notion of solution for variables. He studied this in his thesis. Motion for variables, and actually the thesis that you can find in his webpage, where he rewrote it in LaTeX in a very nice format. You can actually see that many examples, some of which are going to come up today, and that's why I wanted to mention this type of weak solution. However, the solutions that we're going to be considering are not, are Brachie flows, but we're not going to be considering Brachie flows in the most general setting. And I'm gonna mention where the problem that I'm gonna study comes from, that is even previous to Brachy. The work of Brachy is at the end of the 70s, I think 79 or 78. But there's previous work in the context of material science. Mullins was interested in the following problem. So he had some, let's say, domain, I don't know, like some domain omega, and he had a material in two different states. Let's start with two different states in that domain. So you had a domain and you had something coexisting, and and the material naturally what was trying to do was to minimize energy, and the energy that is trying to minimize is something that is proportional to the length of the interface between the two states. So you have like here like a first state and a second state, and the energy is proportional to the length of the interface. Here you should have also some kind of boundary condition that I'm gonna sort of ignore at the moment, but there's also a boundary condition. The interface. And then what you would get in this situation is that, in fact, that interface, because the energy is proportional to the length, is gonna be moving by curve-shortening flow. So it moves by curve-shortening flow. And similarly to this situation, you can have, you would have, that you could have materials that had more than two states. So for instance, I'm gonna draw again a domain. So supposedly you should have some boundary condition here, but that I'm not gonna talk about at the moment. But suppose that you have now three states, three different states. And somehow these three different states have interfaces between them, and you're forming something like this. Then the object that you see there is not longer a curve, because you have this singular point here in between. Although all the pieces that you have forming this are regular curves. So when we're talking about networks, and coming back to my title, a network is gonna be a family of curves that meet at common points that I'm gonna call nodes. So for me, a network is gonna be a family of curves that meet at their ends either other curve of the family or the boundary of the domain. And then the points where the curves meet, with different curves meet, I'm gonna call those nodes. By the way, the meeting points are called nodes. One of the strange things about doing Zoom talks or Zoom classes is that you don't hear the other people, you don't see the other people. So if you have any question, please interrupt me, because it's very difficult to see if I'm going too fast or if I'm losing people. So please just interrupt if necessary, or if I'm not being clear.
And Mariel?
Yeah.
What kind of regularity are you imposing to these curves? Is C infinity, analytic, or what? Or
yes, this is a very good question, and I'm gonna come to that. in a few minutes, but what we're gonna, at the end of the proof, I'm gonna assume that the curves are as regular as you want. And there is a work to show that you can just ask for them to be, let's say, C2. C2 is kind of the minimal regularity that I'm gonna impose in the curves at the end. But for the talk today, due to the time, I think they're gonna be analytic all the way to the end, probably.
Okay.
But thank you for the question. So, okay, so now I need to decide, and I'm going back to that question, I need to sort of say what does it mean, the evolution for something like this. And the curves are gonna be regular, so I'm gonna assume that the curves gamma, I'm gonna call this gamma I, gamma 1, gamma 2, and gamma 3 in this case, but in general I'm gonna have more. The curves are at least C2 to make sense of this. And they move by the network flow, by curve-shortening flow. By curve-shortening flow. If each of them satisfies the equation, okay. They meet at the end. So in my example there, that means that gamma 1 of, let's say, 0t is always equal to gamma 2 of 0t. When you have more, you have to do this for all the nodes, of course, and for all the curves. There's some boundary condition at the boundary of the domain that can be Dirichlet, Neumann. There are many different types of conditions that you can impose there to have a well-posed PDE. For today, I'm going to assume that it's Dirichlet, but it's not very important. Everything that I'm going to say can be replaced by other reasonable boundary conditions at the end. At the boundary of the domain. The other end, I'm going to say just here. But then you get a system of PDEs here. And for this system to be well defined, you need one more condition at the nodes. To have what they call the Lopatinsky-Shapiro condition satisfied, you need one more condition at the nodes. So we need one more condition at the nodes, and this is going to come condition of the node. And this condition is going to come is something that already appears. These flows are actually Brachy flows, and this condition already appears in the Brachy flow, but it also appears in the following sense. So if you have, for instance, just a circle and 3 points on the circle, and you want to find a minimizer for a path that connects these 3 points, that if such thing exists, it's going to be something that looks like this, where these angles are all 120 degrees. And locally, to be minimizing of length means that when I look at the node, that should be also 120 degrees. So in general, for the evolution, I'm gonna need to add one condition, that is the angles forming there 120 degrees, and a way of saying that, and that they meet in 3, so that you cannot have more than 3 curves if you have this condition. One way of saying this is that they meet in group of 3s. They meet in groups of 3. At 120 degree angles, and this is the same thing as saying that the sum of the normals is 0. This is equivalent to that. So there's one more condition that is going to be this, and for the flow to be a regular network flow, we're going to have then that each curve moves by curve-shortening flow, that they meet in group of 3, and that the sum of the normals is 0. And then you have some boundary condition that, as I said, can be different things. For today, I'm not going to really worry about this other boundary condition. a flow with this condition is a bracket flow, but it's something that is more regular really than a bracket flow, because we want the curves to be regular. For bracket, the curves themselves can be variables, and you can have other things that I'm not going to allow for them to happen. You can have loss of mass, for instance, and things like that. So they follow into the category, but they're a bit stronger than that. Okay, so, and by the way, I usually forget to say this, but this is usually known as the herring condition, and comes, I think, Troy Carlo would know better than me about this, but this, I think, comes from like this material science background, the herring condition name. Okay, so let me say a little bit about existence in this case, what is known about existence. And there are several works on this direction about existence. About existence, the papers that are usually quoted are papers by Kinderlehrer and Liu. And Liu. Then there is a paper by Bronzer and Reitig. These are all like, they're quite old papers. And there's one that is now like 15 years old that is here by Carlo Mantegazza, Matteo Noga. And this, I think, Carlo can correct me about this, but this is early 2000s. And then they have a newer one, also where they also talk about existence in this regular case with 3 curves. Many of the things there would generalize to 3 like networks that are regular, I think, just by gluing results. And the first 2 papers, they study the flow with very high compatibility conditions. So they not only ask these things that I asked, but they also ask at the initial time, at least, that the compatibility condition, I mean the meeting, in some sense satisfies the equation. So it's a stronger condition at the node. And this paper that I'm mentioning of the early 2000s, what they do is they or one of the main things that they do is they relax the condition just to require the curves to be C2 and the meeting condition to be satisfied only like at first order. And this is a long approximation argument, and they need several estimates for that. They also have some long time results in these 2 last papers that they basically show that if other singularities don't happen, meaning that, for instance, something that can happen and that I'm going to talk about now, it can happen that one of the curves disappears, that one of the curve collapses. And there are other types of singularities. So if nothing weird happens, then if you have 3 curves, you would be converging to something like the picture that I drew before at the end of the previous page. And I think my screen froze. This happens to me in class a lot, actually. So actually in the most regular case, in some circumstances, you can show that you're actually converging to a picture like the picture I drew here at the end of the page. Okay, but as I said before, you can have singularities. I mean, even if you're looking for minimizers and you draw a circle and you choose your, well, that's not very circular, but if you choose your 3 points very close together, you're not going to have a configuration like I drew before. So even if this is really minimizing, you somehow are going to tend to converge to something that the third curve disappears. Let's say that you fix these endpoints and even you start with something that is very regular, you would expect that one of the curves should disappear. So this kind of singularities can happen, and if you have more nodes, this can even happen inside the network. So you could have things in principle that are, I don't know, like this, and that in finite time would converge to something like this. So this is some, or even more. You could have even more nodes colliding at one and having something like this. Something else that can happen, and these are the pictures that I did try to draw before that I don't know what happened to them. So let's see if I managed to do them like this. I never do very well. If you have loops in your network, if you have a loop like this, you would have, in fact, as in the regular case, that the enclosed area here is collapsing, is decreasing. So this, if nothing else is influencing this, you would expect that in finite time, you're gonna converge to something that is like this, but maybe the angles are the wrong angles, are not already the 120 degrees, because it has to do, I mean, it's related to the shape of this thing contracting, and this may not preserve the 120 degree condition. Or even you could have loops with more sides, and then you would be converging to things again that would have more than 3 curves meeting at one point. This is what we're converging to. There's something also strange in the evolution of networks. I don't know if strange, but different than the regular case, that when you have things that have 6 sides, and 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 sides, actually this preserve the area that is inside. This is a Gauss-Bonnet computation, the same Gauss-Bonnet computation that you do in the regular case, but because you have the nodes, you have an extra contribution. And this thing preserves area during the evolution. So it doesn't change. Area in the evolution. But what could happen during the evolution? What could happen in a situation like this is that one of the sides collapses, and then again you will have a node with multiple things. And when you have more than 6 sides, it doesn't even collapse, the area increases. So if you have many of those in a domain, either sides are collapsing or they are colliding with each other. I mean, something has to be happening if you have many of these loops that have more than 6 sides, because they're going to be increasing. And if you're in a bounded domain, surely you're going to be developing some type of singularities. I mean, this has to happen. Anyway, so all this is sort of to make the point that somehow if you want to continue the evolution here in the way that I defined before, you need to be able to flow out of things that are singular from things that are not regular. So the point of the theorem today is trying to show what happens. I mean, that you can actually have an evolution that starts from something that is not regular. So, and this I also had written before, that was the theorem. So I'm sure I'm gonna forget some hypothesis here, but theorem, if we have a network with C2 curves, let's say, that is not regular at time 0. I'm gonna talk about one node, but with more nodes you can always do gluing results, but I'm gonna stick with one node with not regular initial condition. So I'm gonna make a picture of this. Then there is a solution to the network flow that is regular for positive times. A solution to the network flow that is regular in some short time, 0 epsilon, and the number of solution is classified by the number of self-similar solutions. And I'm going to explain this by the number of similar flows. There are many things here that I need to explain, but let me make a picture before explaining anything. So what I'm going to be thinking about today is some network that has many curves coming out of one node. Each of them is going to be regular. I'm going to impose Dirichlet boundary condition, but this is not very important. And in general, if you have more nodes, you can just do you can do a gluing argument, assuming that you don't have nodes, that is regular enough. That you have a finite number of nodes, let's say, in a domain. You cannot have weird situations like the nodes sort of collapsing with each other in some way. Right? But in regular situations, you should be able to generalize the result easily. One should be. A similar result was previously obtained by Ilman, Neves, and Schulze. So there's a similar result. Their result relies on some stability of the self-similar flows that I have to explain what there are, and we can allow more general things to happen there. And the techniques are different. Somehow our result tries to give a better description of what's happening at the singular point at the node. The first order description is the same as they have, because this is what everyone expected to happen anyway. So this is something that you're gonna need. But somehow what we were trying to do is sort of to give a more precise description of what's happening at the nodes. The methods are different, and this would allow also for a more general class of flows than their case. And I'm gonna try to explain why in a minute. So I think I have like 20 more minutes. And I'm gonna just give an idea of the main result, but before that, maybe, I don't know if anyone has any questions so far.
Mariel, could you say something about what is the meaning of similar flow?
Yes, this is the next thing that I'm gonna explain, and this is a very good question. And this is one of the key ingredients in the proof to understand what are these self-similar flows. And this comes from the following fact: when you're flowing out of something regular, from something that is not regular, from something singular, when you blow up at time 0, you should see something happening there. And the thing that you see happening there is a self-similar flow in the following sense. So let me start with an example that I hope is gonna clarify what I mean by that. Okay, so let me start with an example that at the end is not gonna be an example, but so the example is gonna be this. Suppose now that you have a cross. That's a network. It's a very simple network, but it's a network that is not regular. This example is actually analyzed by Brachy because of the following reason. Actually, if you see the work by Ikera and Husken on graphs, you know that you have a solution that, if you consider just 1/4 of this thing as a graph over like a tilted plane, you know that you have a solution that is like this. And this solution is self-similar in the following way. You can describe that curve there, gamma of xt, as some factor times some fixed curve. Now, it's not very difficult to see if you plug this into the equation that actually the factor is going to be that the lambda t has to be square root of t times something. The usual normalization that you pick, there is a 2, because then when you take derivatives, you're not picking up more 2's. You're taking out the square roots there. You can really take out the 2 and put any number there, but I'm gonna take a 2 to make it nicer. And then a good parameterization to actually see what's happening is that actually gamma of xt, you can parameterize it as square root then of 2t times gamma 0 of x over square root of t. And square root of 2t because I chose a 2 there, square root of 2t. And then what you see, what you understand when you write it like this, is that the two lines are really the tangents at infinity of this fixed curve. So if you look at the tangent at plus infinity, at x going to infinity or x going minus to infinity, then when you see are these two tangents. And then as you have that one, you would have one on the other side. And this is going to be a Brachie solution that, of course, is not a network. And just to talk about the issue of non-uniqueness in the Brachie flow, you can do this, of course, symmetric. You can do it on the other side. So at least in the Brachie sense, you already have two solutions. And Brachie shows that you have one more solution that it looks like this. That it looks like this. There is a graph that is inside the other graphs. And this is a network, and this is actually a regular network. And by regular, I mean that it satisfies the 120-degree conditions at these meeting points. This is going to be inside, actually. I mean, the other solutions are going to be barriers for this self-similar one, and that's why I drew the other ones. I mean, you have some control on how these are converging to the lines, if you understand well the self-similar solutions. These, the pieces of this graph are going to be self-similar solutions that have the same shape. So they're going to be pieces of these other things. And one more thing, because this is completely symmetric, you're going to have also the rotation of that one. This is also going to be a solution. So you can see that in this situation, you're going to have at least two regular networks that are self-similar solutions, meaning that you cannot expect uniqueness. Even in this example, you don't have uniqueness. And somehow, when we say classified by the self-similar solutions, if you have n curves coming out of one point, then the number of self-similar solutions that you have is the number of solutions that we can construct with our method. And this is exactly the number of solutions that you should have. It's an open problem in general to classify how many solutions you have. There are some partial results. For instance, we know that in each case, you can have at most one topological shape. I mean, you can have only one that separates like this. But in general, if the angles are not equal, you could have just one and not one in the other direction. And in some situations that happens. And it's not clear in general. You have an upper bound given by the possible topological classes. But we know that we have at least one, but we don't know how many are there in between. I mean, there could be, for 4, there could be either 2, or in some cases there is 1. And it's not known exactly when both of these things happen. So for this, I'm gonna quote a previous result. I'm gonna add here a previous result. That is exactly what I said. So there's first a theorem by Schnurrer and Schulze that they show that if you have 3 lines, if there are 3 lines, there are 3 lines meeting at any angle. Meeting at any angles. There is a unique self-similar solution coming out of that. In that case, it's unique. With that initial condition. And then there's a result by Rafe and me. with Brave. Given n curves and lines, there is at least one, and here usually is more than one. One regular network, regular self-similar network. Network. With that initial condition. Having said that, the way that we prove that result is that when you insert that form of the curve into the equation, that gives you an equation for gamma zero. Actually, what you know when you write things like this is that gamma zero satisfies that the curvature of gamma zero is gamma zero times the normal. So there's an equation that comes from that, and then self-similar. The self-similar curves are actually geodesics in a given metric. And the way we prove the result is minimizing length in this metric, in this Gaussian metric that is non-complete. But there are some solutions that don't come from our result, and there are more solutions. And you have, in fact, that you can start with, let's say, I think you need at least 6. 3, 4, 5, 6. You can have self-similar solutions that also develop interiors. So you can have self-similar solutions because these are expanding. That for positive times, I'm sure I'm not gonna get the number of sites right, but assume that I did. Yeah, there should be one more somehow here. That can develop an interior. These are not covered by our result, but in our theorem, you can even choose this as a flow out of the network if you want. Probably you don't want that. These are kind of unstable, and maybe this is not what you would want to choose, but you could choose that in our construction. And for instance, in the Ilman and Neves-Schulze construction, they cannot choose things like that. They need things that are stable. So our construction allows also for more types of flow outs. Okay, given that I have very little time, just let me try to give you a rough idea of the proof and where the self-similar solution comes. Idea of the proof. The idea of the proof is something that is very general. So in general, what you try, a way of trying to prove existence is the following, is to construct an approximate solution. A good approximate solution, and I'm gonna say more about this. Then you can linearize around this good solution. Linearize around it, around the approximate solution. And try to solve the real equation by a fixed point method. Okay, so let me explain a little bit each step, and I'm gonna talk more about the approximate solution because this is fixed point argument. So somehow in building the approximate solution, you need to understand very well how the singularity behaves. And this is where the self-similar solution is gonna come in. And this I'm gonna try to explain more. When you linearize, the operator that you're gonna get is one that sort of reflects the conical singularity that you have here, the type of singularity that you have here. And then you need to get for that linear operator good estimates type, like Schauder type estimates for that operator. And that, I'm certainly not gonna have time to talk about that, but that is building on some results that Brave has on conical Ricci flow. So they basically get Schauder estimates in the correct spaces. So you allow a certain type of singular behavior by multiplying by powers of the, this is gonna be clear, more clear in a moment. Due to time, so I think I'm just gonna say a few words on how you construct the approximate solution. What is the idea behind the approximate solution? So one thing about the approximate solution is try to understand in good coordinates what you see. So one thing is to choose the correct set of coordinates. And for that, I'm gonna refer as an example of my self-similar solution. So if you see, you have a square root t factor on the solution, and also on the parametrization. So somehow what we're gonna do is do a blow up of the domain in the following way. So in general, this is the type of method that usually they do in microlocal analysis. So when you have a corner like this, you try to understand better how the corner looks. Normally, something that we are used to do is to describe this in polar coordinates. So you just take r cosine theta, r sine theta. I put the r outside and inside, sine theta. And in normal coordinates, the coordinate at 0 is sort of not well defined somehow. I mean, it doesn't matter what theta does. So somehow a way of describing how you could have different behaviors when you approach, you can include somehow the behavior of theta, and this is sort of equivalent of taking a picture like this. In our situation, this is not, I mean, you still have a half plane. You have the x where you were parameterizing the space variable, and you have the t, but somehow you want to respect also the homogeneity of the equation. So instead of doing these polar coordinates, you're gonna do what they call a parabolic blow up, and that means that instead of taking r to be x squared plus y squared, that's what you usually do, you take r squared to be t plus x squared. So you take a different homogeneity here. And then if you want to describe just the positive part of this, you can do this by taking coordinates x over square root of 2t. I'm gonna put the 2 again there not to have problems with the derivative. You can just choose root t and tau equal to root of 2t. So we're gonna write the equation in these coordinates, but also we need to blow up the range. We need to blow up the curve to be able to see the behavior. So we're gonna think about the curve. Page below. We're gonna think about the curve gamma as being square root of tau, some curve S tau. And now the idea here in the 5 minutes I have, that I'm not gonna be able to explain with all detail, is that we're gonna think that this eta is something that you can write as a power series. So you can write this as tau to some power, eta to some power. Plug this into the equation. You can do this very directly, but of course what you get is not super nice because of the nonlinearity. But if you look at the first term in this expansion, the first term in the expansion that you're gonna see is exactly the self-similar equation. The first, you're gonna get a series of equations. So if you plug it into the equation, and I wrote it here, you're gonna get something like this. You're gonna get that the sum of j eta j plus eta j minus a eta j prime. I'm thinking that this only depends on s. Is gonna be equal to something that is like, I'm missing the tau j here, sorry. Tau j. This is gonna be something that is gonna look like, sorry, I'm not gonna be very precise here, but this is gonna look like something that is eta j prime prime, eta 0, and then you're gonna have an error term. There's a mistake here that I can explain later, but that is gonna depend on the other ones. It's eta 0, eta 1, eta j minus 1. And then the equation for eta 0 is the self-similar equation. So similar equation. So somehow what you're going to have is sort of a recurrent argument that when you choose what eta 0 is, and you can choose any eta 0, you can construct all the other eta j's in terms of this eta 0. You're not, there are a couple of things here. I mean, the error term also have some things depending on eta j that you need to understand well the behavior of the eta j, but that you can also consider them as error term. And somehow I'm not considering here the initial condition. For the initial condition, after you solve this, you're gonna have to change variables to be able to see the initial condition, and you're gonna have to match your our expansion with the initial condition. So the matching can be done very well close to the node, or in general if you have an analytic curve. So I mean, usually what you can do is do it for an analytic curve and then approximate. Okay, so I mean, somehow in this expansion, when you solve for the eta j's, you're gonna have 1 degree of freedom that is gonna be fixed by the initial condition. And because I have just 1 more minute, I think I'm gonna finish here. I had planned to explain this a bit more, but I guess I still don't measure very well the times when with the Zoom thing. Thank you.
Okay, Mariel, thank you very much for your talk, for your very nice talk. And I would like to know if somebody has a question.
Yes, I have a question. Do you need to impose any non-degeneracy condition to the initial condition to be able to solve it?
No, I don't think we need to impose any non-degeneracy condition on that.
I mean, I was thinking on when you do gluing constructions on minimal surfaces, then you do a strategy like the one that you described.
Yeah.
Yes, and then you need some non-degeneracy in order to perturb, no, to a solution, the approximated solution.
Yeah. I mean, in our case, we're thinking that you have some regularity, right? I mean, somehow, so the non-degeneracy comes from the fact that the self-similar solutions are non-degenerate. So somehow you have this problem of this thing being singular at 0, but when you add this hemisphere that I drew in the previous page, you're putting there an extra initial condition that is the self-similar one, the self-similar that you're choosing. The self-similar satisfy, I mean, it's very non-degenerate somehow.
Okay, maybe that's the reason why, yes.
Yeah. There's some estimates, extra estimates that I hid under the carpet somehow. That is how somehow the self-similar solution matches with the initial condition. And that for that you need to work a little bit and show that you have very good decay to the tangent somehow. You need to understand how these two things are gluing as well.
Okay, thanks.
Okay, I have another question. If you come back to the previous slide, where you talk about the matrix results.
Yeah.
Right.
I'm sure this is not going to work because it never works.
Yes, where you had the picture.
Yes.
The other that one.
Yes.
So in these two results, I wonder if the shape of the boundary has any influence on the number of self-similar solutions that you obtain.
Here I'm always thinking about like infinite lines. I don't have a boundary here, so I just have n straight lines and things coming out of that. I'm only thinking about that kind of self-similar solution, because when you blow up in the field that I'm interested about, you're only gonna see infinite lines that are the tangents at that point.
Okay.
So there's no boundary here.
Okay. Hi, Mariel.
Hello.
Could you elaborate a little bit more on the micro-local analysis part?
Sure. I don't know how much you want me to elaborate on that, but so, okay, the point here is that somehow you want to blow up your variables in a way that are compatible with the equation. So usually when you do a parabolic, when you do an elliptic blow up, it's sort of like using polar coordinates. It's like regular polar coordinates, and you're considering the theta variable as an extra boundary somehow. So you're thinking about the picture that I'm gonna paint now in pink, I think. in pink as being your new domain, and you need to add sort of, because you have a new boundary condition, I mean a new boundary, you need to add a new boundary condition. In the parabolic case, the only difference is that you break the homogeneity in the same way that the equation has the homogeneity. So basically you want this, like in the heat equation, you want that x compares to root t. And that's what I'm doing here. And then you're gonna have exactly the same thing. So let me see. This is one set of coordinates. This is not describing the bottom part. You will need another set of coordinates that describes the bottom part, and that could be, for instance, t equal to t, t or square root of what? I mean, let me see, by the way, y squared, y equal to 2x, let's say. Yeah, I don't know how much you want me to elaborate on that, but I could say more. And here, I guess I'm missing the angle variable, but you do it in the same way that you do it there. So you, I always get it wrong. But arc tangent, I think, of theta is usually y over x. And so here is gonna be a square root of t over x, I think. And because I'm putting a 2, then put a 2 there as well. But the 2 is cosmetic, it's not important.
Okay, thank you.
Yeah. I guess you can ask me more later.
I think, Carlo, please go ahead if you want to ask something.
Yes, I have a question. Hi, Mariel, and thanks.
Yeah.
And well, in several situations, when a region collapses, actually, we are not able to have a control on the, in our work, to have a control on the C2 norm of the curves that are then forming a multi-point.
Yes.
So possibly there are situations which are quite interesting to understand if they can restart, where the curves have less regularity, where they are C2 or actually C infinity in the interior, but possibly the C2 norm is going to plus infinity, getting close to the multi-point. And do you think your proof can be pushed to produce a solution even if the curvature is not bounded, getting close to the multi-point?
Oof, that's a very good question, and we did talk a little bit about that with Alessandra. And I mean, she thinks probably you can ask her, and she would know better about this. But she thinks that yes, that it probably can be pushed, but it's certainly not automatic. I mean, you need to see that you can somehow approximate by these solutions that we're building, right?
Because, well, you know, there is this other proof of the similar result by Schulze, Neves, and Irmane, right? In a varifold ambient, and well, I think it's quite different proof, quite complicated actually. I don't know how many people really read it in detail, but I wasn't able at the moment. Well, possibly because I'm lazy, but okay, it's quite complicated and based on different ideas. Well, some different ideas. And well, when speaking with Felix Schulze, he told me that, well, if the curvature is not going to plus infinity too fast, getting close to the multi-point, their proof should be pushed in order to deal also with that case. But actually, well, it's only in the written proof that it's published, they also ask for C2 control. But
yeah, I mean,
that would be very interesting because it's natural. Well, our conjecture is that when you get a region collapse, the curves have actually bounded curvature. So the real singularity is on the curves that are the boundaries of the region which are collapsed down. Instead, the other one should have bounded curvature. But that seems quite difficult at the moment to get this conclusion, where it's a conjecture. So, well, it could be very interesting if, for instance, if the curvature is not blowing up too fast, there is still an existence result even for multi-points with non-bounded curvature.
Yes, I mean, probably you need some conditions, some like L2 norm controlled or something, I would say, of the curvature. I mean.
And also, possibly you already said that, possibly I missed it, in their proof, they ask for a geometric condition that the curves getting to the multipoint has no common tangent vectors. This is
Yeah.
still
No, we don't need that actually. This we don't need in our proof.
so your curves can even have the same tangent getting at the multipoint.
Yeah.
That's good. Thanks.
Yeah, but no, yeah, thank you. You're right. I mean, this would be interesting, but I think it needs a bit more work. It's not automatic, at least.
Well, any more questions? Well, in that case, I would like to thank again Mariel for the talk. Thank you for the invitation. And I would like to say a warm applause.
Thank you very much for the
invitation. In Granada, if possible.
Yeah, well, thank you very much for the invitation. I mean, it's very bad that I cannot see many of you for a long time, but it's nice that at least we can still keep in contact this way. And this has been a good thing about the I guess, the virus, that I've been to many interesting talks by many people.
Okay, then I will stop recording here. See you in the next time. All right. Bye bye.
Bye.
You. Bye.